All right, let's get you ready for those GCSE chemistry exams. You are in the perfect spot. Today, we're jumping into a really important bit of the Using Resources module. We're talking all about the Haber process and NPK fertilizers. It's an amazing topic that shows you how big-time industrial chemistry connects to a huge global challenge. So, let's start with a massive question. Have you ever really stopped to think about how on earth we managed to grow enough food for over 8 billion people? Well, the answer isn't just about tractors and fields. Deep down, it's about chemistry, and that's exactly what we're going to get into right now.
Think about it. We have to grow more food than we ever have before, but it's not like we can just make more planet. So the only solution is to get more out of the land we've got, and that's where fertilizers come in. They're basically chemical power-ups that give plants the essential nutrients they need to grow big and strong. Without them, our fields would just run out of juice, and our food supply would be in big trouble.
Okay, so one of the most vital nutrients for plants, especially for making them green and leafy, is nitrogen. But here's the tricky part, the big chemical puzzle. The air we're breathing right now is almost 80% nitrogen gas, N2. It's literally all around us. But that N2 molecule is ridiculously stable. It has a super strong triple bond holding its two atoms together, and plants just can't crack it. They can't absorb it from the air. That nitrogen has to be fixed, basically turned into a more reactive, usable form, like ammonia.
So how do you solve a puzzle like that on a massive, planet-feeding scale? Well, this is where a couple of geniuses, Fritz Haber and Carl Bosch, step into the story. In the early 1900s, they developed a process that not only won them a Nobel Prize, but also completely changed the game for agriculture and honestly shaped the modern world. It's called the Haber process.
For your exam, you're going to need a really solid definition. So, here it is. The Haber process is the industrial method used to make ammonia by reacting nitrogen with hydrogen. And this ammonia, this NH3, is the absolute key ingredient, the starting point for almost all modern nitrogen-based fertilizers.
Let's walk through this because it's a really clever continuous loop. First up, you grab your raw materials. Nitrogen is just pulled from the air, and hydrogen usually comes from natural gas. Step 2, you crank up the pressure and the heat. We're talking 200 times normal atmospheric pressure and a toasty 450 degrees Celsius. Third, this hot, pressurized gas mix is pumped over an iron catalyst to really get things moving. Fourth, the whole mix is cooled down, and this is a brilliant step because the ammonia turns into a liquid while the other gases don't, so it's easy to separate out. Finally, and this is super efficient, any leftover nitrogen and hydrogen just gets sent right back to the start of the process. Nothing goes to waste.
And here is the reaction in all its glory. You've got one nitrogen molecule reacting with 3 hydrogen molecules to make 2 molecules of ammonia. But I want you to pay really close attention to that double arrow in the middle. That's the secret sauce here. That little symbol means this is a reversible reaction. It means that while nitrogen and hydrogen are busy making ammonia, the ammonia is also breaking back down into nitrogen and hydrogen. And understanding this one little detail is the key to why the conditions for the process are so specific.
You see, in a giant chemical plant in the real world, it's not just about if you can make something. It's about making it fast, making tons of it, and, not going broke in the process. With a reversible reaction like this, it's all about finding the perfect compromise, a real delicate balance, to get the job done right.
And this is where it gets really fascinating. There's a conflict. On one hand, to make the reaction happen fast, you want a high temperature to give the particles loads of energy and high pressure to squish them together. Simple. But to get a high yield of ammonia, things are different. The forward reaction, the one that makes the ammonia, is exothermic. It releases heat. So if you lower the temperature, the reaction says, oh, I'll make more heat to warm things up. And the only way it can do that is by making more ammonia. So you see the dilemma? A fast rate wants it hot, but a high yield wants it cold.
And this right here sums up the whole challenge perfectly. The final conditions they use in factories aren't the absolute best for speed, and they're not the absolute best for getting the most product. They are the best compromise that makes the whole thing work financially. It's a trade-off.
So let's break down that final compromise. The temperature is set at around 450 degrees Celsius. It's kind of like the Goldilocks temperature, hot enough for a decent speed, but not so hot that you kill your yield. The pressure is about 200 atmospheres. Now that's a lot of pressure, and it helps push the reaction towards making more ammonia, but it's not so crazy high that building and running the plant becomes dangerously expensive. And finally, the iron catalyst. It's the real hero. It speeds the whole thing up, which means you can use that lower, more favorable temperature without having to wait forever.
Okay, so we've made our ammonia. We've mastered the Haber process. So what's next? Well, as we've said, its biggest job by far is to go into fertilizers. So let's look at how that ammonia becomes a star player in NPK fertilizers that farmers rely on. You've probably seen NPK written on a bag of fertilizer at a garden center. It's not just a random brand name. Each letter stands for a vital element. N is for nitrogen, which we now know is for great leafy growth. P is for phosphorus, which is crucial for building strong roots. And K is for potassium, which helps the plant stay healthy and produce flowers and fruit. It's basically a perfectly balanced three-course meal for a plant.
So where did these ingredients come from? Well, the N for nitrogen comes from compounds made using our ammonia from the Haber process. Easy enough. The K, potassium, is also pretty straightforward. It's mined from the ground as salts that are already soluble in water. But the P, phosphorus, is a little bit trickier. It's also mined, but is phosphate rock, which is insoluble. Plants can't absorb it. So that rock has to be treated with acid to turn it into soluble phosphate salts that plants can actually drink up through their roots.
All right, deep breath. We have covered a ton of information. So let's boil it all down into one final super fast recap. This is your exam cheat sheet. These are the things you absolutely have to know. Ready?
Let's lock this in. Haber process? It makes ammonia. Raw materials? Nitrogen and hydrogen. Conditions? Iron catalyst, 450 degrees, 200 atmospheres. And the big idea? Those conditions are a compromise between rate and yield. What's the ammonia used for? Making nitrogen fertilizers. What are NPK fertilizers? They've got nitrogen, phosphorus, and potassium compounds. And the detail to remember? P and K are mined, but that phosphate rock has to be treated with acid because it's insoluble. Boom, you've got this.
And we'll finish on this. The Haber process is sometimes called the most important invention of the 20th century. It literally allowed the human population to explode. So it raises this really cool question for us. As we face all the new challenges of our time, like climate change, what do you think will be the next great chemical reaction that transforms our world in the 21st century? Something to think about. Good luck with all your revision.